Hello, everybody. Dr. White here with section 1.5 on Bayes' theorem. We'll start with going back to the roommate problem. So remember, you have a closet, closet A, where 15 out of the 20 pants are jeans and the other 5 are khakis. Your roommate has closet B, where 17 out of the pants are khakis and only 3 are jeans. You get up in the morning, you stumble into a closet, and you only have a 60% chance of going into your own closet and a 40% chance, therefore, of going into your roommate's closet. Okay? And when you go in, you randomly pick a pair of jeans. Your eyes aren't even open yet. So you're going to have a 15 out of 20 chance of picking jeans if you go into closet A. Whereas if you go into closet B, you're going to have only a 3 in 20 chance of picking jeans. And using conditioning, we found out in a previous section the probability that you would end up picking jeans. It was a weighted average of the two probabilities of jeans in each of the closets, and if you compute it, it comes out to 51%. Okay, well, say that you got up this morning and you've done your stuff, and halfway to class, you just finally your eyes open up and you realize that you're wearing khakis. What is the chance that you got those khakis from your roommate's closet? You really want to know this chance because, if it's a really high chance, you're going to double back and very quickly put them back before your roommate wakes up because she gets irritated when you go into her closet. So let's find that chance. So what you're looking for is actually a conditional probability. The probability that you went into closet B given that you see that you're wearing khakis, okay? The probability of B given K. So let's apply the definition of conditional probability. So it's probability of B intersect K over probability of K. And the probability of B intersect K could be written out with the multiplication rule as the probability of B times the probability of K given B. All right, and the probability of K, I suppose, you either have jeans or khakis, so a cheap way to find it would be to go to the probability of jeans that we've already found and do 1 minus that and write in about a 0.49. But let's just remind ourselves of how the conditioning works. So you can find the probability of K by conditioning on whether you went into closet A or B. And it would turn out to be the probability of A times the probability of khakis given A plus the probability of B times the probability of khakis given B, okay? And all of those probabilities are probabilities that you know because you know the closet probabilities and you know the pants given the closet probabilities. And so they're going to help you find this reverse thing of the closet given the pants. So you write in all the numbers that you know, and if you plan on doing these calculations by hand, I'd multiply the top and the bottom by 20 to get this simpler thing. But eventually I just gave up and I went to R and used like a calculator, and I got about 0.73. So think about this. Before you opened your eyes and got evidence, there's a prior probability that you have in mind. There's only a 40% chance that you went into your roommate's closet. The probability of B was 0.4. But then you got evidence. You opened your eyes, you find you're wearing khakis, so you know that this particular event, khakis, has occurred. And you can use that evidence to move to a new probability that we call a posterior probability, posterior for afterwards. The probability of having gone into the closet B given that evidence that you're wearing khakis. And that's higher than before. It's now 73%, maybe enough to convince you that you ought to go back and make it and check and put jeans back in case they are from your roommate. So that's the way of thinking that is suggested by Bayes' theorem. Thomas Bayes was active in the 18th century and came up with this theorem. It's a kind of an overall proposal for how to rationally revise your beliefs in light of new evidence. In a way, after the evidence of having khakis on, you've got new priors now in your mind. If you apply Bayes' theorem situation, you've got new priors. Probability of B is 0.73, so the probability of having gone in your own closet is now 0.27. And in theory, you could keep using Bayes' theorem as you accumulate more evidence to continually revise these, these priors. Your posteriors then sort of substitute and become your new priors, and they're available for further revision in light of new evidence. We'll consider this more deeply later on in the semester. But for now, let's just work up a general Bayes' theorem. So in our situation, there were two events, closet A, closet B, that were mutually exclusive, and they were exhaustive in the sense that they union up to the whole sample space. You had to walk into either closet A or closet B. And they were exclusive because you couldn't have walked into both. Okay? Let's generalize that and say that you've got M events, B1 through Bm, that are mutually exclusive and exhaustive. And then let's let A be any event, and in this theorem, A is like your evidence, okay? Whereas the B1 through the Bm are like these events where you don't know which one of them has occurred, but maybe you have some prior probabilities of their having occurred. And then so suppose that you want to find out, like, what's the posterior probability that BK occurred in light of this evidence A, okay? Then using the same set of computations as we did with the pants example, you'll come up with probability of BK times the probability of A given BK over that conditioning sum at the bottom, which works out to the probability of the A. And you're finding the probability of A by conditioning on the B1 through the Bm. That can be done because of mutually exclusive and exhaustive. So let's check this through by doing the proof. Probability of BK given A is, by definition of conditional probability, that fraction, right? Now, we think of probability of A as a union of M events. The event B1 intersect A through B2 intersect A up to Bm intersect A. Now, that is an exhaustive union of events because, I'm sorry, that's all the ways that A could occur, you know. And the reason is that you have to have done one of the B1 through the Bm. They're exhaustive. So to do A, some BI intersect A has to have occurred. And similarly, if one of these occurs, like if this one occurs, then certainly A occurs. So the event A and this event here really are the same set. They're the same event. So I can just replace the one with the other. Okay. But those events are also exclusive because the BIs are exclusive. I can't do B1 intersect A and B2 intersect A because I can't do B1 and B2 at the same time. Therefore, I can find this probability here by summing up the probabilities of those individual events. And then on the top, I can just use the multiplication rule to get this. And that's what the Bayes formula said. So I'm done with my proof. So let's try just one more example. This is example 3 in section 1.5. Pap smears are a way of screening for breast cancer. I think they're kind of fading out in favor of more powerful cellular level types of tests. But let's take a look at their track record. Pap smears had a false negative rate of 16%. And what does that mean? It means that if you actually did have breast cancer, then there was a 16% chance that the pap smear test would come back negative meaning negative test means, hey, I'm not seeing any evidence here for breast cancer. C plus stands for you got breast cancer. And T minus stands for the event pap smear test came out negative. So you can express the false negative rate mathematically as the probability of T minus given C plus is 0.16. Now, a test can either come back positive or negative, no two other way about it. So 1 minus 0.16 is 0.84. The probability of getting a positive test if you do have cancer is 84%. When you think about women with breast cancer going through pap smears, 84% of them get flagged for further testing and study because their test came back positive, but 16% of them just get missed. And so you kind of hope that like other tests will come along later in the screening process before the cancer gets too advanced. Now, the other thing that you worry about besides false negatives is false positives. And so those are when the test comes back and says, hey, I'm seeing some evidence of breast cancer here, but the person doesn't really have breast cancer. And the history on pap smears is that was 10%, meaning that when a person did not have breast cancer, event C minus, 10% of the time the test came back positive. Okay. Now, another fact is that about 8 out of every 100,000 adult women have breast cancer. So let's say here you are, you're a random person, a random adult woman, and you're planning to go in for pap smear, okay? And you don't know anything about yourself in terms of whether you got cancer or not, okay? You're just a random woman, that's all you know about yourself. So before you get the pap smear, your estimate of the chances that you've got breast cancer, that's P of C plus, would be 8 divided by 100,000, 0.00008. Now, let's say you get yourself your pap smear and it comes back positive. Now, what's your posterior probability for having breast cancer? What is the probability of C plus given that you got your T plus? Okay. Well, applying Bayes' theorem, it's all of this. And we just fill in the numbers that we know. And we come back with still like a pretty small probability. So like when your pap smear comes out positive, it's not like you should immediately go into all these alarms. You still only have about a 7 out of 10,000 chance of having breast cancer. So I'm not even sure, like in practical situations, what would the doctor recommend? Would they recommend going ahead right away for a more expensive biopsy or other type of procedure? Or would they recommend maybe doing another pap smear in a few months, see if that one comes back positive or what? I don't know what the practical resolution would be. It seems like a not very useful test here, but I don't know all the money and medical procedure and system thinking behind whether or not we should still continue to do pap smears. So that's it on Bayes' theorem, and see you later.